Hello everyone, welcome to Flink Forward Global 2021. I am Nagesh Honali. I'm a senior software engineer with Amazon Kinesis. I have been with Amazon Web Services for some time now, and my area of interest has been mostly highly available fault-tolerant distributed systems. Within Kinesis, I work with Amazon Kinesis Data Analytics, where we provide a managed and serverless Flink offering. Today, I will talk about some of the work we have been doing this year towards improving availability of Flink applications on our platform. During this presentation, I'm going to give a brief overview of the managed serverless Flink offering Amazon Kinesis Data Analytics provides and how we deploy applications behind the scenes. Then we will go into our motivation for working on availability improvements and the problems we are trying to solve in this area. We will go over an initial approach we took this year towards high availability, the challenges we faced while implementing them, and then talk about our results. Towards the end, we will also talk about a bit on what we want to do next and the opportunities that lie ahead to improve availability in general. And I would also like to leave about 10 minutes at the end for questions from the audience. Just FYI, I will be referring to Amazon Kinesis Data Analytics as KDA sometimes in the upcoming sections. Amazon Kinesis Data Analytics provides managed serverless Flink offerings where customers can run, stream, and batch processing applications. We provide a platform where customers can rapidly create, test, and deploy real-time analytics applications. While developers focus on application development business logic, we manage infrastructure for them, we provide monitoring and auto recovery of such Flink jobs. We also provide rich and powerful integrations with different AWS services. How do customers build with Amazon Kinesis Data Analytics? So customers can build applications with us in 3 easy steps. They use their IDE of choice and build a code jar that works with a Flink OSS version. Or customers can now use the newly launched interactive notebook interface as part of the KDA Studio console experience to build Flink jobs in SQL, Python, and Scala. Customers can then upload the jar on our platform by using our APIs and then just hit run. KDA then runs these Flink jobs in a fully managed and elastic manner. I'll give you a brief overview of how we run Flink applications on KDA. At a high level, we have control plane and data plane services. Control plane includes a web server that customers interact for synchronous requests. Web server is the component that is serving all our APIs. Control plane also includes application lifecycle management and health monitoring services. Data plane includes infrastructure. For example, we host on Amazon EKS, Elastic Kubernetes Service. Data plane also includes all the prerequisite setup we run to run Flink jobs in a highly available manner. For example, we implement remote state storage integration with Amazon S3, network connectivity integration with Amazon VPC, and any other such integrations we would need to run and scale Flink jobs that happens within a cluster of data plane services. Now, this is an example flow of what happens behind the scenes when a customer hits the start application call. When you call the start application API, our workflow, it assigns the right compute capacity based on parallelism and KPUs. Currently, we are a provision model, so when customers come to our system or come to our platform, they provide parallelism and KPUs as an input, which we use to assign the right compute capacity for your application. We then set up prerequisite services required to run a Flink job in a highly available fashion. So, for example, Zookeeper is set up as part of this workflow. We set up logging and metrics services. We then also set up security and network isolation, VPC connectivity integrations that I talked about previously. The workflow then configures Flink jobs, for example, to run with RocksDB as state backend and Amazon S3 for durable state storage. Then it sets up monitoring and auto healing components that are responsible for scaling and recovering your applications when needed. Now to the main story. We are here to talk about the work our team has been doing to reduce downtime incurred by Flink jobs due to different types of interruptions. In the upcoming sections, we will go into how we have been approaching to achieve a highly available failover of Flink jobs that run on our platform. Now to the problem statement. Security is the topmost feature for Amazon services, and it's especially relevant for Amazon Kinesis Data Analytics because we run customer provided code jars. As you all are aware, in the recent years, the number of security breaches different companies have come to face has significantly increased. For us, the surface area for vulnerabilities in software is even large. This means there's a great potential to exploit customer applications for malicious intent. Therefore, it's very important that we patch all software in a stack regularly. Now, activities like patching introduce interruptions that pause processing for applications. Most of our customer applications, though, is very sensitive to such pauses because they're already actively serving production use cases. So low downtime or low end-to-end processing latency is a crucial requirement for us. I'll explain what I mean by downtime and end-to-end processing latency in just a bit. On top of this, automation of such an activity is also important because of the frequency and criticality of patches. And depending on the criticality, there could be patches where we would have to follow up faster or want them to be available to all applications in a short period of time. So automation is a very crucial requirement for us. While we perform these kind of activities where we are doing system maintenance, we also want to make sure we provide the right visibility to our customers. And in addition to providing the right visibility, we also want to make sure it's a simple experience for customers so it's very easy for them to understand. So essentially, to sum it up, we want a way to update our customer applications with very less downtime. Ideally, we would like to have zero downtime for that matter. And patching is just one example of a frequent activity, but you can think of other maintenance activities. So when we update software, the updates could be to the end customer code because customer asked for it, or it could be our own service code. Now, service code includes software that runs our infrastructure, like the operating system, or the software that runs customers' Flink jobs, or the additions KDA has built on top to provide monitoring and auto recovery services. Any of this software could have vulnerability, or we may just want to keep fixing bugs and adding some features on top of it. So we want to be able to perform all of these kind of updates, causing very low downtime to our customers. Like I said before, most of our customers are they're actively serving production use cases. So they want the processing to pick up where it left off. And this means stateful failover is a must. When we start talking about stateful failover, what kind of state to use for failover becomes important. Should we use a save point or should we use a checkpoint? Similarly, whether we should trigger an on-demand state capture or should we just use whatever is already present also becomes an important decision point. Flink jobs are distributed and customer code runs on multiple EC2 instances. So when we do something like operating system patches, should we perform one full job restart or should we be doing multiple partial job restarts? And this again becomes a important question to answer as well. When do we perform such maintenance activities and how often do we do it? Becomes again another important customer experience requirement for us. So in the upcoming sections, we'll look at each of these decision points and talk about how we went about tackling them. First, let's understand what I mean by downtime or end-to-end latency. Downtime essentially is the time spent by a job not processing data. And we would like to use this term end-to-end latency because that's how customers really perceive it. The downtime shows up as lateness or staleness of computed results to our customers. And these computed results are coming out as output from their jobs. So essentially any job failover has the potential to increase this end-to-end latency. If we look closer, end-to-end latency of a Flink job failover is the cumulative time spent that's split between steps that are in the control of a service provider and those steps which are a function of the job itself. To summarize, it basically includes time spent performing infrastructure setup activities like container scheduling, container image deployment, initialization, etc. It includes time spent downloading customer code and other blobs from remote storage and making it available on Flink. Flink processes like job manager and task manager. It includes the time spent by Flink in taking a save point or a checkpoint and downloading and restoring it on the job. It also includes time spent by Flink, so all operators are caught up to where they left off. For example, task submission, scheduling, initialization, etc. All of that is essentially in the path of downtime for our customers because they add more to the recovery time and how much latency the end customer sees. So if we perform all of these steps sequentially, as shown in the diagram, the end-to-end processing latency becomes very high. You can easily run into a few minutes of latency introduced per failover. And when we start talking about minutes, the definition of real-time processing starts going to risk. So if we need to reduce the end-to-end latency, then we need to do two things. A, identify actions that we can preempt so they're not performed while a job is done. B, identify actions that are independent of each other and execute as many of them in parallel as possible. And that's basically the general approach we took to solve for high availability in the next upcoming slides. So we use a standby Flink cluster to eliminate infrastructure setup time from end-to-end latency. That's the gist of our approach. And by taking the standby Flink cluster approach, we explicitly made a choice of performing one full job restart. So we can limit the downtime to a very particular window. And that way we can also have more control on the failover behavior. The alternate approach we considered was to bring down EC2 instances that run job manager and task managers one by one. But since Flink doesn't fully support partial job failovers for streaming jobs, we found that this approach would introduce multiple job restarts, and it would in effect prolong the downtime window for our customer applications. With the standby Flink cluster approach, at a high level, the failover steps become as follows, right? We run prerequisite steps to make sure we can actually perform the job failover. We then set up a standby Flink cluster. We don't touch anything to do with the currently running Flink job. So we just set up a new standby Flink cluster, and we don't start a new job on it yet. On the currently running Flink job, we induce a save point or a checkpoint. Once the save point and the checkpoint completes, we then stop the old job. This is where the downtime actually starts ticking. Submit a new Flink job on the standby Flink cluster with previously taken save point. And as soon as this job submission succeeds and the new job and the operators actually start processing, that's where the downtime ends. We then mark the new Flink cluster and job as active, and then go on to clean up the old Flink cluster resources. As you can see from the diagram, with this approach, we did two things. We preempted some steps so they can be executed before a job is brought down. And then we perform some steps in parallel instead of the sequential approach. So effectively, during a failover, before we even touch the old job, we bring up a standby Flink cluster and perform all prerequisite infrastructure setup steps. And we then bring the old job down and start a new one. And turns out, just by doing this alone, we realized we saw 4x to 12x improvement in end-to-end latency for our applications. You can also see that in this approach, for a transient time period, we trade off increasing resource consumption in order to achieve improved downtime for our customers. As I mentioned previously, the state artifact we use while we do this failover also has an impact on end-to-end latency. As we all know, Flink supports two types of state artifacts, save points and checkpoints. Save points are full snapshots, and as a consequence, they are resource intensive. On the other hand, checkpoints are incremental, and resource usage wise, they are lightweight comparatively. And from our operational experience, we have found that some applications are ill prepared to support save points because they are not provisioned to handle the order of magnitude difference in state size. What we found out is this means the act of taking a save point itself could actually cause an application to suffer downtime. On top of it, when we looked at our KDA configurations, how customers use our configurations, application configurations, we also found that most of our applications enable frequent checkpointing as frequently as every minute, which is in line with our best practice recommendations. And then and on the other hand, less applications trigger save points on a regular basis. Save points are portable across code changes, parallelism changes, etc. However, checkpoints have limitations on portability. So we considered all these different trade-offs, and we ended up using the artifact that actually favors low downtime the most. And based on the data we looked at, essentially we decided to use checkpoints most of the times. Most of the scenarios we picked checkpoints, the most recent ones. And in their absence, then we revert to using save points. Another decision point for us was to identify how to pick the most recent save point or a checkpoint. You could say there are two types of Flink failovers. Usually two types of failovers in general, an abrupt failover and a graceful failover. In an abrupt failover, like for example, when an EC2 instance goes down, Flink restores a job from the most recent save point or a checkpoint that's found in its zookeeper index. However, in a graceful failover, usually customers of Flink induce a save point on demand, and then they go on to use that to start a new job. We wanted to combine the benefits of both abrupt and graceful failover. For instance, if we trigger a save point or checkpoint on demand, there's actually a potential to cause downtime to application, thereby affecting its availability. And as I said before, this can be because like the customer has under provisioned that application, or they have some code problems that end up failing the save point. And all of these kind of failures would only mean that our workflows would have to have more retry scenarios to handle, which would only prolong the end-to-end latency for the application. So we decided to reuse the most recently completed save point or checkpoint, just like what happens in an abrupt failover behavior, like an EC2 instance going down. We then combine it with a graceful failover approach because we control how and when a job is stopped. So essentially combining the benefits of both the approaches into one. While we worked on these availability improvements, we also wanted to make it easier for customers to have visibility and configurability of these maintenance activities. So Amazon Kinesis Data Analytics introduced a new application state transition called maintenance. Before we touch the currently running Flink job, we move the application state to maintenance. We perform a highly available failover and then move it back to running. We also introduced what we call as maintenance windows. A maintenance window is essentially a time period during which a KDA application could go into maintenance due to patches, bug fixes, etc. And as part of implementing maintenance windows, we choose non-peak periods in every region to run maintenance activities. And that's the default option you get when you create applications with KDA. Now we did talk to a few customers, and we understood that some customers would need flexibility in defining these windows. So we allow customization of these default windows as well. While designing this solution and looking into the problem, we ran into a few challenges. For example, how do we use checkpoints to failover? Because there's a lot of lack of portability for that matter when you talk about checkpoints. It could so happen that when a customer change is happening, customer is changing their code and using our update APIs, it could race with a maintenance activity that the system is running, and which would render the checkpoint incompatible, especially if there are changes to job graph. Then how do we retain checkpoint metadata outside of Zookeeper? So our failover workflows can be fault tolerant and idempotently retry. How do we support the same behavior for all the different Flink OSS versions that KDA supports? And then how do we support highly available failover for different job types. Like we have streaming job type, batch job type, and then we have Python jobs that we support. How can we make sure the behavior is the same and simple in all these different scenarios? And because we provide a managed offering, it's not just about submitting a new job for us, but KDA also makes sure that the new job is running fine as it was before we even touched it. So different job types makes it interesting to identify and perform error classifications during job submissions. And one of the other challenges was, how do we measure overall downtime or end-to-end latency? Because now we have potentially have two jobs that are running for an application, and two Flink clusters that are running for an application during this transient time. And how do we make sure we attribute the right time spent towards the overall downtime for that application? To recap, here are all the optimizations we ended up implementing. We choose the most recent already present save point or checkpoint, so it's not on demand triggered. Since our configurations use frequent checkpointing, there's a very high probability that we are going to end up using a checkpoint for failover as opposed to a save point. We then circumvent the checkpointing portability by locking the application state, so there are no compatibility issues. This is what helps us guarantees that we use checkpoints for failover. We bring up a standby Flink cluster before starting the old job. And along the same lines, we download and upload code artifacts and other blobs to Job Manager before we stop the old job. And just by doing these simple optimizations, we realized that our end-to-end latencies improved by a factor of 4x to 12x, depending on the application profile. So in our first milestone, what would take 120 plus seconds of downtime per application, it went down to 10 to 30 seconds for a majority of our applications. We now have a regular and automated deployment driven by criticality of patches, and these significantly reduce our customers' exposure to vulnerabilities. We also provide customization of maintenance windows, so customers can define what their non-peak time means. We ended up keeping the familiar simple failover behavior, so everything is simple enough and customers are not confused about what's happening when these maintenance activities are happening. And lastly, we ended up building and tracking granular visibility into downtime incurred, which we would like to start using for some of the future improvements that we would like to make in this area. Our first milestone is really an incremental step towards where we want to go. Like I said in the beginning, ideally we want zero end-to-end latency for our customer applications, and no matter what kind of an update that's happening. So we would like to continue to work on these improvements. These are some of the things that we've been thinking through as to what our next steps are along these lines. And as you can see, there are only a couple of things that are KDA specific, but rest of them are improvements we can make to the Flink overall open source code base. So we would like to collaborate with the community where possible to make it happen. For instance, on the KDA specific ones, there is opportunity for KDA to apply these optimizations to all types of updates, not just system maintenance activities. And similarly, we want to improve heuristics on reducing the staleness of a selected save point or checkpoint. Because we are not triggering on demand, The worst case scenario could be that we end up picking a save point or a checkpoint which is very old. So there's an opportunity to make it better. For example, let's say there's an ongoing save point or a checkpoint. Our workflows could wait before even starting the failover process. And within the wider Flink community, there are a lot more optimization opportunities. There is opportunity to reduce the time spent distributing code and state artifacts and other blobs to job manager and task managers by actually prefetching them before taking down the old job. And for example, we can use transactional stop job with save point or checkpoint, so it reduces the amount of replay a job has to perform. And we found that this actually favors exactly once processing as well, with sinks in place. Similarly, we want to address portability concerns of checkpoints and resource use limitations of save points. So effectively, what we want is a lightweight, portable state snapshot. So it could be as much as thinking about it as an incremental save point. And I believe Flink has some of these in the flips I mentioned here. There's also improvement to be made about the availability of save point or checkpoint index data. What we have found is the life cycle of this index, like what is the most recent save point or checkpoint, actually is dependent on the infrastructure. For example, if you delete the Kubernetes cluster, the checkpoint index goes away in Zookeeper. So we are thinking about something along the lines of a high availability service connector, where we could store this data. It could be like using Amazon S3, for example. Then there are improvements we can make to batch jobs. There are certain limitations with batch jobs on how save points and checkpoints work with them. And I believe Flink has some ongoing discussions in a flip about this as well. And lastly, we found that the interactions for Flink Python job submissions are not similar as others. So we'd like to make some improvements to make sure the job submission behavior is in par with other job submission behaviors. Overall, we believe there are more interesting problems yet to be solved in this space, and we really would like to continue to collaborate with the Flink community where possible, so we all move towards zero end-to-end latency for Flink job failovers. With this, I would like to conclude my talk and thank you for providing me the opportunity to present today. Thank you for listening. I would now like to open up this session for the audience if there are any questions.